Lesson 6 here. Gay-Lussac's law. Okay, there, we got over it. All right, that's his name. Okay, relax. When a sample of gas, we've looked at pressure and volume and temperature. Now we're going to focus on pressure and temperature. This one's probably the most easiest one to understand, because I think most of you guys can probably relate to this one. When a sample of gas has its temperature changed, the pressure is going to change. So temperature changes, the pressure has to change as well. Okay? Often you see this in car tires. You're driving down the street, when you measure them, they look flat in the morning, yeah, sometimes when it's cold, right? And you say, hey, look, it looks flat. Not good, right? You measure the pressure, it's low. Temperature's low, pressure's low. You start driving down the street, friction, right? They start to warm up. They warm up, you check them again when you get to Calgary, the pressure's gone up, right? Pressure, temperature. Pressure low, pressure high, temperature is going to be high, okay? Those two are related. The volume stays the same. The volume of the tire never changes, eh? Like, people always get confused. Oh, the volume changes. Yeah, it looks flat because there's less collisions. The volume of the tire doesn't change. There's still the same amount of, there's still gas in there, okay? If you don't fill up the car tire, you don't put any more gas into the car tire, assuming it's completely sealed, which it's probably not. But you never put, that doesn't change. It's the temperature when you're driving, right? It increases, more collisions, more pressure. More pressure, when you measure it on the pressure gauge, you get more pressure, right? The volume's still the same. So that's a Gay-Lussac's law, all right? We used to give you a written response question on that. Mostly you see this with a solid tank, so something that doesn't change. If you have a propane tank, those little camping propane tanks, the ones I'm talking about, the little Coleman's, little green ones, they're tiny, right? Think about that. You got your little tank here with your little nozzle there or whatever kind of thing. If you think about this, okay, if the volume's 5 liters here, and then you take that same tank, volume 5 liters, okay, and if you're talking about pressure and temperature, you start out and you put that tank of that cylinder of gas in the freezer downstairs, and then let's say it gets down to minus 20 degrees Celsius. You put that in minus 20 degrees Celsius, guess what? If you measured the pressure in that tank, there would be very little collisions probably taking place. Okay? The pressure is going to be really low because, remember, this tells you, the temperature tells you in this case, molecules are moving very, very slowly. Yes? Especially at minus 20. Molecules are moving slowly. If they're moving slowly, there's not going to be many collisions. If there's not many collisions, there's not much pressure. Pressure low. Yes? This is the most straightforward one. Okay? We have to understand this one. You take that cylinder out of the freezer. You go camping. You think it's a good idea to throw it in the fire. That's not a good idea. That's a bad idea. That's kind of stupid. Okay? Then the temperature goes up, right? Temperature starts to increase. You're giving those molecules of gas more energy. They start going faster and faster and faster. More collisions, more collisions, more collisions. The pressure goes up. Now, hopefully the fire is not hot enough to basically make the pressure exceed what the walls of that container can hold. Hopefully. But who knows? So, what happens when the temperature goes up so much, the pressure gets so intense inside of there, that at some point something's got to give. So if the steel is not strong enough to hold that, it goes kablammy! Right? It blows up eventually. Because what other choice does it have? Right? It's only as strong as the steel is going to hold it in. Guess what happens after it goes kablammy? The pressure inside equals the pressure outside. They've equalized again. Okay? It's just not a good way of doing it. All right? So, we can go back to all the other stuff. Pressure inside equals pressure outside. Right? So, that's Gay-Lussac's law. Right? Same container. You take away temperature, you're slowing down gas molecules. You put energy in, You're speeding them up, you're going to get more pressure. That's it. That's Gay-Lussac's law. There's a graph for that as well, by the way. It looks like this. Pressure and temperature. Okay. There's a formula that goes with this as well. Formula looks like this. P1 T1 equals P2 T2. Okay. It's a direct relationship between the two of them, pressure and temperature. When we talk about P1 T1, we're talking about the initial pressure, initial temperature, and the final pressure and the final temperature. Okay, P2 and T2. Once again, notice this formula does pressure and temperature. Volume has to stay the same. Look at my cylinders, both 5 liters. Okay, so volume has to stay the same. Has to be a closed system. You can't let the gas escape. Otherwise, it's not true anymore. And the temperature, of course, has to be in Kelvin, as always, for the rest of this year. Okay? So those are the 3 conditions. All right? That is Gay-Lussac's law.